All right. So thanks everyone for joining. Arvind is my good friend, and he's also chair of Geoenvironmental Engineering Committee of Geo Institute ASCE. So, and it's nice of him to take time to moderate today's webinar. So, so I wanted to share, uh, one of our ongoing research projects with you. So this is related to biochar and addressing mixed contamination in urban stormwater runoff. So it's a little bit different than traditional geotech topic or geoenvironmental topic, but you see that a lot of things you learn in geoenvironmental, for example, permeable reactive barriers that we look at for groundwater treatment could be applied here. Actually, application of it is much simpler than doing in situ groundwater treatment. So my presentation topic is biochar-based filtration and barrier systems for mitigation of mixed contaminants in urban stormwater runoff. So as many of you know, I work on environmental remediation of soil, sediments, groundwater, and stormwater. I also work on waste management and landfill engineering, life cycle assessment, and sustainable and resilient engineering, and also geotechnical engineering. It's always challenging to select a topic because I love all these topics. And you can find more information on this website, but today's topic is one of the topics that I work on related to stormwater. So as you may be seeing it personally yourself or watching on TV, flooding is becoming extremely a huge problem, especially in urban environments. You see all kinds of damage happening, not at in one country or one location. You can see this one is happening worldwide. It could be China, Ukraine, Africa, India. I mean, any country I can take. I can find some of these pictures to show a lot of flooding and a lot of damage to infrastructure, life coming to standstill, basically, right? And even in the US, we have this flooding problem in many cities. As you see, a few examples, New Jersey, North Carolina, Vermont, Louisiana. So, again, this is very prevalent and a lot of damage and a lot of issues associated with this urban flooding. And it's not only just the infrastructure and other things, people really affected, on a personal basis, right? Their houses gets flooded, especially if they have a basement, everything gets flooded. A lot of their things are damaged. And sometimes, the houses are not livable. So on a really personal level, the damage associated with urban flooding is so severe. I think, sometimes when you see these pictures like this one, it's a really, you feel sad or, it's a, you want to do something, for these kind of situations. And Chicago is not an exception. Again, a couple of years ago, we had a severe flooding and showing the pictures of different areas in Chicago, city of Chicago, Austin and Cicero and Pilsen areas. And as you see here, people are affected on a personal basis. Their houses, everything that they possessed, got affected. And the affected areas are communities with low incomes, and again, this adds on to the burden to their daily life. So this is really, an important issue to address as human beings. So if you look at statistics, the disasters in general are increasing with time due to climate change and other issues. As you see here, disasters could be floods or storms or landslides or let me put my pointer. Or droughts or extreme temperatures as you see here. But this blue is the flood situation. And you can see among all the disasters, floods are the most common natural extreme weather events worldwide. We talk about a lot of, these different disasters, but the floods are, predominantly the major issue. And as you see with the statistics, these floods are increasing. It's not just the coastal floods, but inland floods. You see all kinds of issues. It's just not if you are inland, doesn't mean that you're not prone to flooding problems. So it's really a huge problem. And in the US, if you look at annual loss due to floods, the darker it is, the more damage that you have. So, you can see certain parts of the US, you see tremendous loss due to flooding. And the figure on the right side you see is the insurance premium increases, because when you have a flooding, the insurance companies jack up their premiums. And you see here, the premiums have increased to 35%, in some areas. And if you look at who has the insurance, only 18% of properties at risk for flooding are insured. So, what happens if you have flooding and you get damage and, basically you don't have insurance. So that really, causes a lot of personal issues financially, to cope up with the problem. So the flooding, a lot of times you're flooding, you think about, a lot of water gushing into your basements and, in your neighborhoods. But actually we have a, bigger problem than just amount of water gushing into your basements. So the water that is gushing into, or like the stormwater we call it, or stormwater runoff we call it, could be contaminated. So think about that. You have so much of water, so you could have a sewer backup, and it could be mixed with the stormwater. Now you have polluted water that is entering into your houses. And on the roads, you have cars, there's going to be oil leaks, all that contamination is getting into runoff and then getting into the houses on the roads. And you could have a toxic chemicals, that could be mixed with, running water and litter, waste, all that could be entering into the stormwater drainage. And the stormwater, could be contaminated, or even on the surfaces, you could have all these things, and the runoff could be interacting with them and then causing the problems. So, generally you have a rainfall and you have a stormwater runoff, and then that gets into drainage systems. And in a controlled way, we want to kind of discharge into the surface water bodies. But the conventional systems that we have now, they are not sufficient. That's the problem. They are not designed for these extreme flood events that are happening. So that's why we are having a lot of issues. As I say, like a pollution is the problem, and where does the pollution come up? Because as I mentioned, a few things in the previous slide, but in general, it could be, vehicles, industries, construction activities, sewage, and, even the fertilizers in the landscaping areas. So some of the contamination could be airborne, and then when it's raining, that gets onto the surfaces and into the stormwater. And polluted surfaces or contamination could be on the surface that gets carried away with the stormwater. So the contamination happens because of these two reasons, and then the stormwater gets contaminated, and that gets into the drainage systems. If the drainage systems are not adequate, then it gets into the houses and causes all kinds of problems. So all these pollutants that you see here, they are very toxic. They can cause a lot of health issues. So it's really a concerning situation. So we have a paper, we kind of discussed these issues in this. So what kind of contamination you have? Of course, it depends upon, the location where you are in. But in the US, we have this database, and that has the information about stormwater influent concentrations and effluent concentrations. Basically, this is like best management practices, database, and they're trying to look at what solutions can work to address this contamination. So in this database, they have all those different options, but also has like an inlet concentration. That's basically concentrations in the typical urban stormwater. So if you look at that one, you can find all kinds of contamination. So this is the real data from the field. You can get, for example, if I want to know the lead concentration, you can see the range of concentrations that are found. So similarly, you can pick what concentration what contaminant you are interested in, and it can display the contamination that is found that is measured in the stormwater. So it is not one particular type of contaminant that is going to be present. You will have a mixed contaminants because the stormwater is passing through different areas, mixing up with different areas. So you're going to see all these contaminants and many more. I'm just showing you some selected metals here and nutrients here, and then some organics here. And I'm giving you the range that the concentrations of that are found. That sometimes these higher ranges are really of a major concern. So I have just listed a few of them, but you can find a comprehensive list in the publications or in the database. And this was like old data, but this is the new data that we are finding it from recent publications. People are starting to report all this information. And then, one of the things that you have to worry about is, okay, you have concentrations, but what should be the limits, right? So you should look at site-specific or location-specific regulatory limits on type of contaminants and the concentrations. So basically, the goal should be to reduce the concentrations from high levels to the acceptable levels by these regulations. So now the question is, we know the problem. I mean, I hope you agree that urban stormwater issues is a concern, and if we do something, actually, we are doing something good for the humanity. So what can we do? What are the engineering solutions? As I pointed out, the existing stormwater management systems are not adequate, okay? And they're not designed for these extreme events. So, and also, going with the same traditional systems is not, sustainable, So now the more emphasis is on green infrastructure. And green infrastructure can solve the flooding problem as well as, could address the pollution that we are talking about. And, these can be done on an individual basis as well as, as a society in general. For example, if you have a house, you could have a green roof, stormwater systems and downspout disconnection, rain garden. So all these things will help reduce the runoff. And in the public areas, you want to think about these permeable pavements, if you have roadways or sidewalks. And then these are the ones, it's called roadside rain garden or bioretention swales or bioswales. And then you have trees and other things that you can use. There are, different options under green infrastructure. So the purpose of all these things is to allow infiltration of the rainwater into the ground so that we don't create the surface runoff. And also these systems, if they're designed properly, they can, treat the contamination also. So that's kind of a way, like the cities are looking into. So you might have seen these kind of things, in your cities, in your neighborhoods, these are called bioswales, So they are engineered systems, they're just not simply, putting some plants and to make it look nice. Of course, they look nice, but also they are engineered. So the way they engineer is that, yeah, you dig a trench and then you slope it so that, the runoff can get into this. And then you put a engineered soil or filter media. So when the infiltration happens, contamination gets removed, and it should be permeable enough so that it can infiltrate down. And then if you have a permeable subsurface, it could just it could recharge the groundwater. If not, you may have to have some kind of a drainage system, perforated pipes, and all that flow that coming into that could be diverted and discharged into surface water source. So in this one, of course, this media that you use here is very important. It has to be permeable so that water can infiltrate really fast. And also, it should be able to remove the contamination so that the water that you collect at the bottom, eventually you are discharging into the surface water, that is clean. So this bioswales is very commonly used. As I mentioned, vegetative channels capture and convey the stormwater runoff, encourage infiltration and drainage to reduce the runoff. As the water infiltrates, contaminants are absorbed into filter media. So this filter media is very important. The other option is these are called infiltration trenches. You're probably seeing these along the roadways like this one. So basically, you have aggregate surface cover, and below that is you have a filter media. And then again, simply, you are letting runoff enter into this infiltration systems as it infiltrates down, okay, because it's the, permeable material, so it infiltrates down easily. And then it goes to this, the filter media, and then you can let it, you can discharge into the subsurface, or you can have a collection system to discharge into nearby surface water source. So again, you're trying to infiltrate so that reducing the runoff, and with proper selection of the filter media, you are treating the contamination, and then the water that gets infiltrated downward, could recharge the groundwater or safely collected and discharged into the surface waters. So that's the idea of this one. In some areas, semi-urban areas, you see this constructed wetlands. So you see the picture on the right side. Next time when you're walking around in your neighborhood, observe all these things, because these are all not landscaping features. They are actually engineered systems to address the stormwater. So basically, you have stormwater coming in here, and you have these plants, wetland plants, that take out the contamination. Basically, it's like a phyto remediation. And then and you could have some filter media inside here also to retain the contamination. And then the treated water can be discharged. So this is kind of more nature-based, and you see the usefulness of wetlands and wetland protection. So it's very important. So this is, again, you want to make sure you have organic substances or some filter media here so that contamination can be absorbed. And some of could be removed by the plants. So you will have a combination of processes to remove contamination. So filter media, in all these applications, one of the important things is to make sure it has a high permeability, and it should be able to take out the different types of contaminants. And the material that you choose should be locally available. It should be low cost, and you should be able to replace them if needed, because all of these have some finite life. So you need like periodic replacement, and they should be environmentally sustainable, low carbon footprint, and low environmental impacts. So if you look at literature or actual projects that are done, there are different types of filter media used. So I listed few of them here. These are very commonly used. And but if you look and evaluate carefully, each of these have some limitations. So our task was, hey, all these things have limitations. Can we think about any other new material as a filter material? So biochar, we have been working with biochar for other applications, for example, in landfill cover systems and so forth. Say, can we use this biochar as a filter material for stormwater applications? So that was our idea. And I don't know how many of you are familiar with biochar. This is becoming very, very popular term. So, just want to give you a brief background to biochar. So there is no universally accepted definition. The International Biochar Initiative has a particular definition. We used to have a US Biochar Initiative, but that became recently American Biochar Institute that has its own definition. But without worrying about these fancy definitions, common definition is carbonaceous material produced from the thermal decomposition of organic matter in the absence of in the absence or limited supply of oxygen. So simply, it is a material. You take the organic matter and you thermally decompose it, and then the residual carbonaceous material is the biochar. So how it is produced is basically you take any organic biomass, you see here, and put it in this pyrolysis plant and you heat it up. And then you get this syngas and pyrolysis oil. So a lot of people in chemical engineering, in other fields, they are interested in creating biofuels from organic mass or the organic waste, basically. So they are more interested in this one. But in this process, we get the biochar. They don't care. They think this as like a waste material. People who trying to harvest this biofuel from this organic mass. But for us, it's like, hey, this is not a waste. This is a great material that we could use in our civil and environmental engineering applications. So the pyrolysis units, they work under different temperature conditions. So there should not be any oxygen. And then these can work from 300 to 800 degrees centigrade. There are two methods of pyrolysis. One is called the slow pyrolysis. So in this case, you start increase the temperature gradually, and then heat up the organic mass. But there is a fast pyrolysis process. In this one, you suddenly increase the temperature to the maximum level, and then burn it, right? And depending upon whether you're doing the slow pyrolysis or the fast pyrolysis, the biochar, the amount of biochar, and also the quality of the biochar varies. So it's very important to know that distinction. One thing I like about this biochar is, you could take whatever local biomass that is available. It could be anything. It could be as simple as, weeds and, any kind of organic matter that you can take it. And I like about this biochar because you can have a small scale barrels. You can create your own, and then you can create a biochar in this one. Or lab scale, you see some of the researchers, they use fancy lab scale units and generate the biochar under controlled conditions, because for the research, you need to have a controlled biochar production. And then you can have these small scale units, and also you have a large scale unit. So the point I'm trying to say is, the biochar production can be scalable. If you have a small project in your neighborhood, you don't need these fancy things. You can just create your own and use your biomass and then make the biochar right at the plant. There are, just for your information, there are other methods of producing the biochar. There's gasification, hydrothermal carbonation, liquefaction. So just for your information, if you are looking in the literature, there are different methods. And in terms of the biomass, we call it a feedstock for pyrolysis units. You can see, I just show you some examples of, all the waste materials that we generate, and they could all serve as organic waste. So here, you could have a wood-based biomass. I'm giving you these examples here, and we create a lot of waste wood. And then these are like a plant-based in agricultural waste, grass, weed that we generate, especially in agricultural waste. There's so much of waste that we generate, we don't know what to do with those things. And these could be really useful feedstock for creating the biochar. And then, animal products, again, you can see all these things. And, these are all the waste materials, So if we can convert these waste materials into good use, right? And, we are producing the biofuel and also biochar. So we're going to address, important problem of waste management and also creating a new material, a new energy. It's like win-win for everybody. So how does the biochar looks? It could look in different forms. Generally, they are all blackish or dark gray in color. And depending upon the pyrolysis process, you could see, different physical forms. So biochars have really very unique properties. So you have a unique chemical properties, you have unique physical properties. I can talk about all these things in detail, but I don't have time. But these unique properties makes this biochar very unique material to apply in engineering applications, and including the environmental remediation applications. So and people are exploiting the unique properties of biochar for different applications. So they are adding to the soil, and they are using it as a carbon sequestration material, contamination removal, as I'm presenting today, and it's even being used in construction material as an amendment. And then, not only in civil and environmental engineering, people are also using in electrical and chemical engineering applications too. So there are a lot of applications about this one. So if you create the biochar and you found that it is not having the properties that you really want, you don't have to give up. You can just modify the biochar by additional treatment. So this could be a physical treatment, it could be a chemical treatment, it could be biological treatment, it could be magnetic modification, or you can, add some amendments. So you can modify biochar with any of these methods to create the conditions that you are looking for. So biochar can be engineered to suit your application. So that's what I'm trying to mention. So again, I presented all this information in one of these papers, so you will have more information on this. So those who are interested in using the biochar or interested in doing research with the biochar, pay attention to, some of these considerations. No two biochars are the same, so you cannot really say, I'm using this. If somebody use this biochar and then you think, your biochar will perform the same way. No, they are going to be dependent upon the feedstock and pyrolysis conditions. There is no standardization for biochar production. And, as I said, you can actually create this biochar on site, but it depends upon transport distance, feedstock, that determines the feasibility or cost of the biochar. And careful selection and characterization is very important before you start applying biochar. And as I told you, locally sourced feedstock and local production would reduce the cost, the environmental impacts. And as I said, hey, if you don't find the properties, you can engineer or modify the biochar to tailor your needs. So And so I gave a presentation on this one. It's on our YouTube channel. You can look at that one. There is a tremendous interest in biochar, using the biochar in many applications. So I just want you to pay attention to this one. I just typed biochar in my search, and then I found so many publications. As you see here, so these bar charts are the number of publications per year. So if you go back to 2011, 2012, see there are just a few of them. And look at recently, last year, 2025, how many publications we have? 10,000 publications are somehow related to biochar. 2024, you see this one. And if I add up cumulative, we have more than 50,000 publications. So look at this trend, it's exponentially increasing. So, if you, didn't do any research on biochar, and whatever research that you're doing, see, what is magic about this biochar, and think if you can use it in your applications. So, yeah, don't be ignorant about biochar. There's so much of research going on for so many applications. So it's kind of nice to know, what is going on this. So as I mentioned at UIC, we have been using biochar for many different applications. And today I'm going to, present about how biochar could be used as a filter media in stormwater or green infrastructure applications, right? So in a bioswale or infiltration trenches, if I want to use biochar as a filter media, does it work, right? For stormwater and mixed contaminants. So that's my research objective. So we evaluated 6 ag-based biochars. These are all, something corn, hemp stalk, pine wood, walnut shells, almond shells, rice husk. So these are the 6 biochars we selected. And, these agricultural waste products are available everywhere. And so you can use them as a feedstocks. So these are the 6 we tested in our research. Important thing is to characterize them. So for organic content or carbon content, and also hydraulic conductivity. If we are using this one in bioswales or infiltration trenches, you should have a permeability equivalent to that of pea gravel or coarse sand. So you see 10 to the power -2, -3 centimeter per second. That meets the permeability requirement. Now, most important thing is, can these remove the contamination? So we tested with 2 contaminants, phosphate and nitrate. These are the common nutrients of concern, of environmental concern. So here you can see the results. These are the 6 biochars, and you see the results, right? They all remove phosphate, but you see, they remove to different extents. And this is the nitrate, and you don't see the same trend as the phosphate, right? So some of them have very low, the one which is removing more phosphate doesn't necessarily remove more nitrate. So, but you see, they are all removing to a certain extent, but the extent of removal really depends upon the type of biochar. So there's a significant variability in absorption removal capacities of these biochar. So that's why I want you to pay attention to the characteristics of the biochar. So just don't say I have biochar and it will work. So it really depends upon that. Now you can do some fundamental investigation on how the contamination is being removed. So here, there are different processes that we think are at play. So one is the physical absorption. It could be contaminations are trapped in the pores of biochar. You could have a surface complexation and precipitation happening. Phosphate could precipitate with the metal ions present on the biochar surfaces. Electrostatic interactions could be at play in acidic pH. Negatively charged phosphate and nitrate interact with protonated functional groups. You could have an anion exchange taking place, exchange with the weakly bound anions on the biochar surfaces. And you could have a ligand exchange. You can phosphate could replace OH or protonated OH2 plus group. So, a lot of these things could be, at play at the same time, depending upon the contamination that you have. So if you have a mixed contamination, different mechanisms will come into picture. So as I told you, testing with phosphate alone or nitrate alone is not going to give you a good picture of applicability to field conditions, because in the field we have a mixed contaminants. I told you we have a lot of metals, a lot of nutrients, a lot of organics, even organic contamination also, and total suspended solids. So we did testing. We created this synthetic stormwater. We know this is the range that you find in the stormwater, but we try to, keep it high concentrations. If it can work for high concentrations, it will work for low concentrations. That's our philosophy behind, using the high concentrations in synthetic stormwater. So when you add all these chemicals to the water, this is the cocktail mix you will find it. It looks good, but it's a dangerous, solution. So we did the column experiments. Basically, we have a biochar here, and we have a filter material or pea gravel on both sides, and then we inject that synthetic stormwater through here, and it's passing through this biochar, and we collect it and see how much. We know the concentrations, inlet concentrations. What are the concentrations that is coming out? So we were able to determine, for this one particular waste pine wood biochar, these are the contamination removal efficiencies that we found. So the thing that I want to mention is you're not looking for 90%, 100% removal, okay? So you need to reduce the concentrations from these high levels to the acceptable levels, right? So that's why you need to actually, instead of percentages, you need to look at the concentration level, the initial concentration, and then what the final concentration. So you can see these removal efficiencies. Not all of them are removed, as you see here. And then this is regarding the metals. Again, some metals have been removed extensively, like a lead, for example, and copper. But you have a very low chromium and nickel. So you really need to pay attention to this one. So this is for one particular biochar. Don't expect the same results for another biochar based on another feedstock, or maybe you have a modified biochar that could actually remove a lot of these contaminations to the larger extent. So, but this kind of testing is important before you actually use it in the field. And as I told you, modification could be necessary depending upon your biochar. For example, in one of our studies, we modified biochar with iron 3. As you see here, if you don't have iron modification, then you have a low phosphate, nutrient removal. But when you add it, 1% or 5% or 10% iron chloride solution, you can see the removal increases significantly. And then we tested this modified biochar on actual stormwater that is collected from different parts of New Delhi in India. This work is in collaboration with Delhi Technical University. And you can see, this modified biochar was more efficient than unmodified biochar. In our research, what we are doing is, using chitosan as amendment to biochar. And we are very interested in working with chitosan, because this is also, the biochar is produced from the waste material as a waste biomass, right? And the chitosan is also is derived from waste materials. It's a polymer. It's derived from shells of crustaceans such as shrimp, crab, and lobsters. You see in the, all these things, that's basically created as a waste. And from that, you create a chitin, and from chitin, you create a chitosan. And this has a really promising ability to absorb a wide range of contaminants, heavy metals, organics, dyes, nutrients, because it provides abundant functional groups, amine groups, and hydroxyl groups. So the chemistry between these functional groups and the contaminants uh, could help remove multiple types of contaminants to the maximum extent. So this is the review paper that summarizes all the work that people have done in the past. And then we kept on doing additional research on biochars that are amended with chitosan. So important thing is how do you amend biochar with a chitosan? You really need to follow a specific process, synthesizing process, and then make sure that chitosan is coated properly on the biochar, and it will help avoid excessive pore filling, and even after amendment. It should possess the hydraulic conductivity because we need hydraulic conductivity for infiltration to take place. So as I mentioned, chitosan functionalization enhances ion interaction. And as you see from here, a smooth surface of biochar you see versus on the right side, you see the rough surface of a chitosan amended biochar. So we tested this chitosan amended biochar for the phosphate and lead. So phosphate is a representative anionic species. As you see here, this is the biochar alone, right? And then there's the solid circle is the biochar alone, and we have another biochar because we have two feedstocks. So they give you similar results. But when you add chitosan amendment, you can see this one is a Constav biochar modified, so it increases removal, and the other one increases even more. So this clearly shows that chitosan amendment improves the removal, and that removal depends upon the type of biochar you're using, right? And then, okay, on this side, lead absorption. So these are the two biochars that I mentioned here. And then here is the chitosan amended biochars. So the two biochars, behave similarly, unamended versus amended. But you clearly see that amendment actually increases significantly, right? So which is good. So this chitosan is really helping to enhance the removal of lead, right? And interesting thing is, this is the cationic contaminant. This is the anionic contaminant. So with the amendment, right? So we are able to remove not only anionic contaminant, but also cationic contaminant, which is not easily done with these adsorbents generally. So adsorbents, could be effective for, cations, but they may not be effective for anionic contaminants. So with the amendment, you can see that we could remove both of them. So because, in stormwater, we have mixed contaminants. We have anions and cations. So we are trying to find an adsorbent that can remove both anions and cations, right? So that's a really important aspect. So adding chitosan helps to remove both anionic and cation species. That's kind of a unique aspect that we are looking for it. I want to give you, we can do a lot of lab research, right? But how do we translate the research to the field scenario? So in Chicago, we have stormwater connected to the, our underground, tunnel and reservoir system. But along the lakeshore, we don't have the system connected to the existing sewer system. So what happens is when it rains, all the water near the lake gets into the lake, right? As you see from here. So when a lot of suddenly the storm happens, the water gushes into the. So this picture shows clearly what happens, and then all the contaminants that you have in the stormwater is getting into the lake, and it has become a big problem because in Chicago during the summer we monitor the quality of the water, and if the quality of the water is not good, then they close the beaches. So number of beach closure days are increasing because of these stormwater events, and then potentially contaminating. So what is the solution? So what we said is, instead of directly discharging, why don't you pass through the filter system? So this could be underground filter. So at the surface you cannot do anything because there are a lot of people using the space. So you could have an underground filter. So you can have that stormwater infiltrate into this underground filter, and then it passes through the filter, and then it comes out, and then it can be discharged into the lake, right? So basically, instead of directly discharging the contaminated water to the lake, we can just discharge the treated groundwater, right? So, and it is a high permeability flow, and it removes a lot of different contaminants. Outflow can be directly put that one, so it really helps. So, and we looked at one site. It's called Rainbow Beach on the south side of Chicago, and we mapped all the areas, and then we constructed this one. This is our filter, basically concrete tank. And it's supposed to be underground, but since it's a research project, we just built it on the top near the ground surface. And then you can see this side is the inlet, and this side is the outlet. So when it's raining, water goes inside here, and it passes through the filter and it comes out. So we were able to collect the water here at the inlet, and we collect the water from here, and then we could see the reduction in the concentration. So important thing in these kind of projects is, when it rains, you need to get this first flush. You need to be ready to collect the samples here. So whenever the sky looks cloudy, going to rain, my research assistants have to run there with samplers and then wait for the rain to happen and collect the water sample. Sometimes, it does not rain at all. So it's kind of a fun thing. But it's a nice place, having a project on the beach, even if it doesn't rain, even if you spend hours and hours waiting for the rain, that's not waste of time. So from Rainbow Beach, you can see a good view of Chicago downtown. Very beautiful. So these are my research assistants. We finished this project, and we really got good results out of this one, to demonstrate that these things actually could be used not only for this lake application, but any surface water source, rivers and other things, right at the edges, you can create these underground filter systems and pass the water. So I want to go through quickly the other side of the application, since I don't have much time. So I hope you understood that the filtration system. So now the filtration systems may not be enough to handle so much of water that is coming at a time. So we need like some storage systems. I know storage systems are very hard to have in urban environment because we don't have a lot of space. But these could, you could have a local stormwater retention ponds, and in suburban semi-urban areas you will have these kind of things available. So a lot of times, these retention ponds, the water goes into there, and then you store there, and then slowly release it. Now, what we are saying is that we cannot have these unlined, because before we used to have a clean water going into this one, so it's not a big problem. But now, because we have a lot of contaminants, we need to have a liner or some kind of a barrier at the bottom, so contamination does not seep into the ground and cause the contaminated groundwater. So we are basically suggesting that we should have some kind of a liner at the bottom. If not, just a regular storm water, but especially if you are in nearby, industrial areas, where contamination is going to be very heavy, and it becomes extremely important to have this one, because definitely you will see a lot of contamination in those areas. It's just almost like an impoundment, industrial impoundment. So in this scenarios, basically we're talking about having a liner system at the bottom. So it should have a low hydraulic conductivity. this is the barrier system. So it's a reverse situation compared to the filter system. In the filter system, you want the water to go through. Here you don't want water to go through. And you need to have contamination retention properties, ease of installation, durability, long-term performance. So all these things that you learn for landfill liners or impoundments, come into play. So we use these kind of liner materials, bentonite-based materials. Most of them, we use the bentonite and, add it with other things. But the problem is bentonite-based liners are not effective for the different types of contaminants that I mentioned before. So you have metals, salts, hydrocarbons, nutrients, these are, different sizes and different charges, and they have different chemistry, under different pH conditions. If I increase the pH, it's good for something, it's not good for other things. Ionic strength, dissolved substances. So these conventional bentonite-based liner materials are not efficient or effective to remove this wide range of contaminants that we expect in the stormwater. So that really made us think about using this chitosan. And of course, we need to have a bentonite. Without bentonite, you cannot get low permeability. So can we add, bentonite, chitosan to bentonite? So we say, okay, chitosan, bentonite composite. So how does it improve? It should maintain the low hydraulic conductivity and also improve the contamination removal capacity. Then we said, okay, why don't we think about bentonite and the biochar composite, right? So that could really, how does that help? And then, obviously, next question is can we add chitosan and biochar to bentonite and create a composite that could be effective for removing all the contaminants? So we came up with a very good synthesis process for all these things. We created these materials. One is called chitosan bentonite composite. And then, when you add chitosan to bentonite, we think, this chitosan replaces the metal ions between the bentonite layers. Basically, it intercalates in the bentonite. And it adds positive charged functional groups, like amine groups, as I mentioned before, to the composite. And it reduces the swelling. Then you should think about whether that will affect your hydraulic conductivity. So that's what and it increases the permeability and, the swelling. And then on the other hand, if I just add biochar to bentonite, what happens? Biochar gets distributed in the bentonite matrix, and the biochar, particles act like a solid reinforcing phase material, and actually it gives you the mechanical strength. The functional groups are there in bentonite. That could help in removal of certain contaminants. And so there's, there's a limited addition of positive functional groups. So no significant improvement in anion interaction because, just about like how we saw for chitosan, that was a positive thing that you don't see it here. So we see the positives of adding these things. And then if you add all of them, chitosan and biochar to bentonite, you're going to realize the benefits of biochar as well as benefits of chitosan. So that can help, because you have a bentonite, it could help reduce the hydraulic conductivity and also remove the contaminants. So basically, we created these chitosan amended bentonite, biochar amended bentonite, and then chitosan and biochar amended bentonite. So these are the materials we synthesized and we characterized them, and then we tested them. So for phosphate removal, as you see here, so this, just want to show you this for phosphate. This is the bentonite, right? The first, the solid circle is the bentonite. And then you see, if you add the biochar, it increases a little bit. But if you add chitosan, it improves significantly. This is the highest. If I add biochar and chitosan, it's slightly less than just the chitosan alone, right? So chitosan actually helps a lot. So you have a maximum removal. But again, this is the anionic species. What about lead? Is a cationic species. You see this one is a bentonite is here at the bottom, and then biochar amended chitosan amended bentonite here. It does not do that much good, but biochar here helps a lot, right? And then chitosan and biochar amended one gives you really good performance. So you see the conflicting things, but when you add all of them together, so consistently you're getting a really high anionic removal, and simultaneously you are getting high cation removal. Otherwise, you would not have gotten both of them, right? So you would have gotten good results for one and not good results for other one, as we saw for just if you add bentonite or just you add chitosan. So again, with these things, you can see that adding two of the materials, chitosan and biochar, and we call it CBBC composite, is really good. And there are, we investigated the mechanisms. I don't want to go into the details of this one. What we think is happening, contaminant removal mechanisms for anionic species, for cationic species, and then okay, we need to do this long-term column experiments, and then so we are running these flexible wall permeameters and column tests. Basically, we created these cylindrical samples. We are flushing the synthetic stormwater and collecting the water outside. And with that one, we are able to measure the hydraulic conductivity and also trying to analyze the effluent to see the contaminant transport. So we have a lot of these tests going on right now, but I wanted to just show you just the sample results. So this is in the actual test. One is just the bentonite itself, and the other one is chitosan biochar amended bentonite. As you see, both of them, having the very low hydraulic conductivity. So the hydraulic conductivity wise, they are similar, but the advantage of CBBC is to remove the contamination. But as you see, we ran the test for 322 days, right? So look at, you need to have a lot of patience when you are dealing with low permeable materials. You cannot, accelerate. So I admire my graduate student, Banu, for patiently measuring this and continuing to run. So we may have to go for a longer time, but even like I'm showing you the effluent data, we don't see the trace of contamination coming out from effluent. So there's a lot of absorption capacity in these materials, and it will take really, really long time for seeing the breakthrough. And our anticipation is that, bentonite alone or unmodified bentonite, you will see breakthrough earlier than CBBC. But we cannot wait for that long, so we're trying to do some, simple batch experiments to find out the relative performance, as we see here, for example, nitrate, bentonite alone, but the CBBC with the two different types of biochars, you can see, it's definitely improvement in the removal capacities. So in all these filtration systems and barrier systems, hey, you need to pay attention. These are not like, you can just mix it and use it. You really have to, I don't have time to go through this one, but there are different considerations you need to think about before you apply them. There's a paper, and we can send that one to you. So in closing comments, so traditional stormwater management methods often fail to effectively address urban flooding and runoff contamination. So we need to have engineered stormwater management systems, and biochar and chitosan amended biochar can serve as a sustainable filter materials, and chitosan amended bentonite and chitosan biochar amended bentonite can be sustainable barrier materials. And as I was mentioning, you really need to pay attention to the properties of biochar, properties of chitosan, properties of even bentonite, needs careful attention. So more field studies with performance monitoring are needed. So again, I want to thank my graduate research assistants and for the funding from Chicago Park District, US EPA, National Science Foundation, and collaborators. And these are my lab websites. You can look at for the publications and more information with that one. So these are kind of a very closely related publications to the presentation content that I have, so I can provide this information to you. So with that one, I want to thank you for your attention. I know I took a little bit longer time, but I hope I gave you the information, the most essential information that you need. Uh, thanks everyone. So
Okay. Thank you, Krishna. That was a very comprehensive and informative presentation, wonderful presentation. So let's open the floor for questions.